We can also articulate other things like bounded safety. Can anyone besides you and me ever get access? Or liveness. Will there always be somebody that has access? Or mutual exclusion. Can anyone ever be both a buyer and an accountant? Now, all of the ones that I've listed so far have the characteristic that they compare the membership of a role to a constant set of principles. In the last two, we actually will compare two different classes or roles. So we can say, for instance, will all managers always have access? So we're comparing managers and those that have access. And in the very last one, can anyone who is not an employee ever get access? So these have, respectively, the flavor of availability and safety. So to make the problem concrete, we study it in RT0. And policy states are given by RT0 policies. The restriction rule that I talked about, which defines how policies can evolve in an uncontrolled way, is given by two sets. G, which is a set of roles that whose definitions are assumed not to grow during the course of uncontrolled evolution, and shrink-restricted sets S, which the analysis assumes will not have their statements removed or their definitions removed from the state. There are going to be three different forms of queries: membership, boundedness, and containment. You'll notice that membership and boundedness, basically, they compare a given role, A.R, to a specific set of given principles, D1 through Dn. So on the left, we ask whether A.R, on the first one, we ask whether A.R contains D1 through Dn as a subset. And in the other case, we ask whether A.R is bounded by the set D1 through Dn. Now, the third is actually strictly more general. It asks whether the role x.u contains A.R as a subset, and it can be used to capture membership and boundedness queries, but we distinguish it we distinguish the first two cases because they can actually be solved in polynomial time, as we'll see. So let me just work a couple of examples for you quickly. The idea here, I'm going to give you a policy and a restriction rule, and then we'll pose a couple of queries and see how it works. The idea here is that the system administrator, SA, has a resource, and he grants access to the resource to everybody that HR says is a manager, and to everybody that a manager says should have access, provided that person is an employee. HR says you're an employee if you're a manager or a programmer. Alice is a manager. Bob and Carl are programmers. And Alice says that Bob should have access. So currently, Bob does have access. And then G and S define the restriction rule, and we'll play with them in a minute. The first example asks a simple safety query. Is it possible that Eve should gain access to the resource? And the answer to this is yes, because the first statement up there says that any manager has access, and we can HR can add a statement defining HR.manager at any time in an uncontrolled way. So the analysis has to take that into consideration. And the reason that we know it can add it in an uncontrolled way is that HR.manager is not included in G. The second query asks a simple availability question. Is it necessary that Alice has access? Will she always have access? And the answer to that is, again, yes, because of the two statements shown in red here give Alice access now, and the fact that they both define shrink-restricted roles means that those clauses or those statements won't go away in the future. So the third example illustrates containment, the most powerful form. It asks whether those who can get access are always going to be employees. And the answer to this turns out to be yes. Basically, there's no way to get access besides by these first two rules. And that's because SA access is growth restricted. So we won't get any more statements defining it. If you gain access by using the second rule, you're clearly an employee because of this intersection. And if you gain it by the first, then you're a manager, and by the third statement, you are therefore an employee, and that employee definition is not going to go away because this is shrink restricted. So that's going to remain the case. So let me give you an idea of how this can be used. I mean, this is one of many possibilities. An organization has many principals to whom it entrusts the preservation of the policy state, but it has some ideas of sanity checks for what a good policy ought to do. You know, bad guys shouldn't get access, and key guys should have access to critical resources, that kind of thing. So what the organization does is he formalizes these as analysis problems together with acceptable answers, either yes or no, and then trusts the principals in his organization to run the analysis before they actually make any policy changes, and only commit the changes if they will preserve the requirements. So the evaluation of membership and boundedness queries can be done efficiently by using two non-standard logic programming semantics for program P. And I won't go into them here. Containment queries, on the other hand, their complexity, or the complexity of the analysis problem, depends on the sublanguage. So if we call this basic RT, it contains only facts and simple delegations. RT with linking, RT with intersection, and RT with both is just all of RT0. And here are the results. It turns out that there are polynomial algorithms for basic RT. And then if you add linking, the complexity jumps up to p-space complete. If you add intersection, it becomes co-NP complete. And if you add both, we don't have a lower bound, but we know it's in co-non-deterministic exponential time. Okay, so at this point, I want to switch gears and talk about the fact that when using credentials in order to gain authorization in an open system, you may not wish to trust the recipient of these credentials with everything you've got, because the credentials themselves may be sensitive. We want a way to establish trust between strangers that somehow preserves the privacy requirements on the sensitive attributes and shares them only with authorized entities. So the approach that we take is really somewhat simplistic, but it seems to work quite well in most cases. Credentials are treated as protected resources. So access control policies are established for them just like they are for other protected resources. And then automated trust negotiation is our technique that consists of a bilateral credential exchange in which the negotiators seek to establish mutual trust incrementally. Now, the simplest strategy that you can use for this is called the eager strategy. In it, negotiators take turns sending all the unlocked credentials. So negotiator 1 sends all the credentials that he basically considers public information. Then negotiator 2 replies with all of his public credentials plus any that have been unlocked by negotiators